So let's see how to do this, working things out the way we've been working things out. And so what we're going to do is we're going to put these vectors as a linear combination of each other. So let's do that. We can set up the equation, but we'll see after a while how we can transform from these vectors directly into a matrix without setting up the equation. But let's make connections first. So we got x sub 1, 5, 0, 0, plus x sub 2, 7, 2, minus 6, plus x sub 3, 9, 4, negative 8, equal to the 0 vector. And I'll put a vector on top saying this is a three-dimensional vector because all the other vectors in 3D. And so we're looking at the 0 vector. Again, not that we need to, but translating this is actually a system of linear equations. We got 5x1 plus 7x2 plus 9x3 is equal to 0. 0x1 plus 2x2 plus 4x3 is equal to 0. And 0x1 minus 6x2 plus, or let's call that a negative 8x3 is equal to 0. So again, this is not the way we want to go, but I just want to point out that there's these relationship between these vectors and the system of linear equations and stuff. So let's see if we can go from here. And writing this as a matrix, or writing this as a matrix of coefficients, we can simply write the matrix 5, 0, 0 going down, looking at the columns. 7 minus 2, 7 positive 2, 6, negative 6, and 9, 4, negative 8. Now this is a system with an augmented right-hand side, but the right-hand side is all zeros. This is a homogeneous system, so we can choose to just ignore the zeros and work this out, or you can put zeros there if you want. But from now on, if we know that it's equal to 0, we can just work with the left-hand side of the system and assume that there is going to be zeros in your augmented portion. All right, so we can do things, and to simplify this, so we can get a solution. And so let's, looks like, we might as well just go straight at it. Let's multiply the second row by 3, right? That would knock off the third row. So 3 times the second row added to the third row. And then from now on, I usually put arrow R3 to say I'm going to replace a third row, but from now on, it should be clear that we're replacing the second row, that's R3. Or the second R something that you see, which is R3. So 5, 7, 9, the first row doesn't change. 0, 2, 4, this one doesn't change either unless we want to, in our heads, multiply it by 1/2, but we'll keep it like that. 0, 0, so this is the point, is to make this a row reduce or row echelon. And so we have 0 for the second element in the third row, and then positive 3 times 4 is 12. 12 plus negative 8 is 4, I think. So whatever it is, it looks like it's in reduced row. It looks like it's in row echelon form, and you can just take it from here. So now that we have a row echelon form, we see that we can solve, or we can back solve for x3, x2, and x1. So we have 4x3 is equal to 0, which says that x3 is equal to 0. And then we got 2x2 plus 4x3, which is equal to 0, and that's equal to 0. So x2 is equal to 0. And then you'll see that x1 is also equal to 0. So we have a trivial solution. And what does that mean if we have a trivial solution again? Yeah, your solution is 0, 0, 0. But what does that mean for the problem that we're looking at? It's linearly independent. So trivial solution vectors are linearly independent. Okay, questions? Let's do another example. Let's see what happens if they actually are linearly dependent and what the result should look like or could look like possibly. So let's do another example. In this example, we have 3 vectors again. We want to check if they're linearly independent. So you see that stuff in the red, we can kind of, go through that process, or we know that all we're really concerned about are the make these into column vectors and put them in the columns of a matrix, right? So we'll skip over that step and jump to making this into a system and then a matrix of a homogeneous system where you just write these vectors down as a column. So 1, 2, 3, 4, 5, 6, 2, 1, 0. Essentially, that's what we're doing. So we want to reduce, and let's do a couple of steps here. Let's take R1, multiply it by -2, add it to row 2, and let's take the same row 1, multiply it by -3, add it to row 3. So 1, 4, 2 for the first row. The second row, we're multiplying the first row by -2 and adding it. So that's going to give us a 0 here. That's what we want. So -2 times 4 is -8. -8 plus 5 is -3. And -4 plus 1 is -3. What? Did I do something wrong? Was good? Okay. The third row, I'm going to multiply the first row by -3 and add it to the third row. That would give me a 0. -3 times 4 is -12. -12 plus 6 is -6. -3 times 2 is -6 plus 0 is -6. And you can kind of see that the third and fourth rows are already equal to 0. So we can just say we'll multiply the second row by -2 and add it to the third row. 1, 4, 2, 0, -3, and 0, 0, 0. Okay, so looks like we have a free variable. And when we have a free variable, you know that you have a solution because you can let that free variable x3 equal to whatever you want. So we have a solution. And you can write the solution as a parameterized solution, parameterized by something. If you think back in what we've been doing the last couple of days, you should think about how to write this. I'm not going to go through that right now because I just want to make sure that we have a non-trivial solution. So if we have a non-trivial solution, that means we can find values for x1, x2, and x3 and write this as a linear combination that's not equal to 0. Let me say that again. You can find values for x1, x2, and x3 so that a linear combination of these things with x1, x2, and x3 equal to 0 would give you a non-zero solution for x1, x2, x3. Yeah. Okay. So vectors are linearly dependent. Okay. So let's see if we can get a visual of what this means. If we're still in 3 dimensions, which means we can still picture this. So let's take a look at the first 3 vectors and see what they mean by linearly independent. What does it mean for the vectors to be linearly independent? Ooh, I have to remember how to do vectors. V1 equals vector start end. I think I would just put a point there. I'll be good. 5, 0, 0. Like getting this vector? Nope. Vector 5, 0, 0. There we go. This vector shown here, it looks like it's one of the axes, and that makes sense because x is 5, y is 0, and z is 0, so it goes along the x-axis. So that's 5, 0, 0. So v2 equals vector and 7, 2 minus 6, and v3 equals vector 9, 4, negative 8. So if we take a look at these vectors and see what they look like, I don't know if there's anything telling about these vectors. Can't really see anything interesting about these vectors. They are linearly independent. So we want to try to get an idea of what it means visually for 2 or maybe 3-dimensional vectors, what it means for them to be linearly independent. And so right now I can't see anything that's interesting to say about them. But maybe if we take a look at the linearly dependent ones, we can come back to this and see what it really means to be linearly independent versus dependent graphically. So for these vectors now, let's call it V, where are we? 3, V4 equals a vector 1, 2, 3. V5 is the vector 4, 5, 6. And V6 equals the vector 2, 1, 0. So now let's see if we can find something interesting about something that's linearly dependent in 3 dimensions. Does that look? Can you see that? What'd you say, Malcolm? They look like they all might be on the same plane, right? So we have these vectors, and they look like it's on the same plane. Let's maybe change the color of this one red, just so I know which vector is which. The red vector is the 4, 5, 6 one. The 1, 2, 3. The 2, 1, 0. The 2, 1, 0 is on the xy plane. Z is equal to 0. So when z is equal to 0, you're just on the xy plane. So that's this vector here. And so that must make the other vector 1, 2, 3. Okay, so they're all on the same plane. Let's see if we can actually make sure that they're all on the same plane. Plane. What kinds of things can I do? Line, line, point, point. Let's put all those 3 points in there. 1, 2, 3, 4, 5, 6. And what was the last one? 2, 1, 0. This is our plane. And if we look at it flatly, you see that these 3 vectors are all on the plane. Let's get rid of the xy plane just so we can focus on this. So we see that these 3 vectors lie on a two-dimensional plane. I'm stressing the two-dimensional part of it because when we study more dimension stuff, that'll be important to note that a plane is a two-dimensional object, and I have three vectors that are on this two-dimensional plane. So that I think that makes it linearly dependent. So now let's go back to the other picture, the three vectors that we have here. Are they all on the same plane? Does it look like it? It doesn't look like they're all on the same plane. Trying to find an angle that would get these three vectors all lined up together, and I can't seem to find a viewpoint that would give me all three vectors all lying on the same plane. So it looks like these three vectors do not lie in the same plane. So visually, in 3 dimensions, in R3, if you have three vectors that all lie on the same plane, then they're linearly dependent. And if you have three vectors that don't lie in the same plane, then they are independent. All right? Does that make sense? Okay, cool. So yeah, I think I can, if you want to take these examples and take a look at them from home, I'm going to, I think I could find a link. I have to save it. I'll do that later. Yeah. With the weights with x1 v1 plus x2 v2 is equal to 0. I don't understand the differences between those two equations. Okay, well, the thing is that we found, so I didn't want to do this, but let's do it. We found this to be linearly dependent. So that means I should be able to find weights for 1, 2, 3, 4, 5, 6, 2, 1, 0. I should be able to find values for these things that would set this equal to 0, right? That's the point. And again, I skipped this way of writing it, but if I were to write it like this, we're essentially solving for x1, x2, and x3. And we said that we found a non-trivial solution, x1, x2, and x3. So let's work it out. Let's see if we can find it. So let me continue solving for this. I have x3, I said was free. So x2 minus 3x2 plus, well, let's say negative 3x3 is equal to 0. I could just divide out the negative x3 and bring the x3, or negative 3, and I'll bring the x3 over to the other side. So x2 equals negative x3. So let me box these so I don't lose them, and then we'll put it together in a few minutes. So x1 plus 4x2 plus 2x3 is equal to 0. Let's bring everything over to the other side. x1 is equal to negative 4. x2 is actually negative x3, right? So let's put negative x3 there, minus 2x3. So what does this turn out to be? x1 is equal to (2x3), right? Positive 2x3. So that's my solution set, and x3 is free, which means I get an infinite number of solutions. So my solution, you write my solution in red. Not that you can see red. Can you guys distinguish the colors? IT people are not fixing. So our solution, our x vector solution, would be x1 is going to be 2x3, negative x3, and x3. And that's, if I take the x3 out, or if I could change it to t or whatever, then that's my parameter. So if I let x3 equal to 0, it's going to be 0, the trivial solution. I'm not interested in that. So the next nicest number is 1. So if I let x3 equal to 1, then I have a solution. X is a solution. It would be 2 minus 1, 1, right? So if I put 2 minus 1 and 1 in these slots, I should get this to work out. That's a non-zero, non-trivial solution that makes these things equal to 0. You can go ahead and check that. Is that true? All right. Yeah. Well, if I plug in this vector is all equal to 0, so it's not. I don't think it's going to lie on the plane. Let's see. -2 or 2, -1, 1. Let's throw that in there. This is the one, right? Yep. So let's throw another vector, v, where are we now? 6, 7, v7. What was it again? 2, 1, 1. Yeah, so that vector does not lie on the plane. It's the weights that we're looking at. So those make up the weights for the other vectors to carry. Yeah, so this wouldn't go with us. And by the way, since we have an infinite number of solutions, if I let x equal, or let x3 equal to -1, then my solution would look like -2, +1, -1. And if I were to put those numbers in, -2, +1, -1, I would still get this to equal to 0. And you can double check that, either in your head or write it down. You'll see that it actually would work also. So regardless of what the solutions are, because we have an infinite number of solutions here, we can have a variety of different combinations of x1, x2, and x3 that would get this to equal to 0. Bottom line, these vectors are not linearly independent. Okay? Questions? Yes. So the only way it could be linearly independent is that if you work this out in your solution 0, 0, 0. There's no way to get these three vectors when you add them and scale them, add them, subtract them, whatever, scale them, to get back to 0 unless you scale them by 0 in the first place. Yeah. The what function? Uh-huh. Well, I don't quite understand your question. Yeah. Yeah. Well, the plane, oh, here, the plane looks like this. It's minus x plus 2y minus z is equal to 0. So that's the equation of the plane that we have there. The way I created this plane in GeoGebra is that GeoGebra has a variety of ways of making drawing a plane, and one of the ways is that if you have 3 points, that would define a plane. And so with those 3 points, I made a plane, and this happens to be the plane. Now, there's a vector -1, 2, -1, which is going to be perpendicular to that plane, but that's beyond what we're doing here. If you've taken Calc 3, that sounds familiar, but we're not doing that here. Yeah. Oh, for an independent set, so one thing about this plane is that this plane passes through the origin. So the origin is kind of like a 4th point. All right. So in here, if we try to do that plane thing the way we did that plane thing with the other one, what were the points again here for the independent set? 5, 0, 0, 7, 2, minus 6, 9, 4, negative 8. And what this is going to do is, according to GeoGebra, it's going to be a plane that passes through those 3 points, and those points are vectors. But for this to actually, let me get rid of that XY plane again. So this, if you take a look at the plane, it passes through the tips of those 3 vectors. Now, for this to be linearly dependent, it also has to pass through 0, which it doesn't. Okay. All right. Any other questions? Okay. So now that we got the idea and the calculations needed for checking if something's linearly independent or dependent, let's make a note of what we've already noticed. Note what we noticed. More on. So again, they want you to always have in the back of your mind the relationship between working with vectors, treating the vectors as if they were columns, and going back to your systems of equation, and in your systems of equation, being able to write it in vector form. So all those things are all related to each other, and by being able to find the relationships between these different things will allow us to see, you know, how we can take advantage of some of the things that we're looking for in linear algebra. And bottom line is that we work with matrices. It's related to this to vectors. It's related to systems of linear equations, and etc. We'll find more relations with other different things as we move along. But we know this already, right? We took those vectors, we made them into columns, and we found if they're linearly independent. We also wrote it as a system of linear equations. So it's all there. Let's take a look at special cases where we take a look at 1 or 2 vectors. The example that we did had 3 vectors, but it was the case where you're looking at only 1 vector or only 2 vectors. It's easy to kind of see whether they're linearly independent. Okay, a set of only 1 vector is linearly independent if and only if it's not the 0 vector. If it's a 0 vector, I can put a weight of anything I want, and that's going to equal to 0. So that's like trivial. If it's non-zero, then the only way you can make that equal to 0. It's a silly thing to do, but to make sure all the mathematics is covered, I don't even know what's right for that. No, yeah, I do. So if your set is just a vector v, then x1 times v is equal to 0. If either v itself is equal to 0 or x1 is equal to 0. So the case where v is equal to 0, the 0 vector that is, then that means I can put in a non-zero value for x1, and so that would make it dependent. So the 0 vector by itself is technically dependent with itself. But any other non-zero vectors, if v does not equal to 0, then that means x1 has to be equal to 0, and that's a trivial solution. So that's the only way that'll equal to 0. So if we have two vectors, whether you're in 2 dimensions, 3 dimensions, or any higher dimensions, a set of two vectors is going to be linearly dependent if one of the vectors is a linear combination of the other. It's just a scalar multiple. So the only way they can be independent is that if you can't find a number that's scaled. So in other words, if you can write v1 is equal to some scalar times v2, if you can find a scalar, and I'm using alpha for a scalar, I don't know why, but if you have a scalar that you can put into for alpha, where you can make this equation true, then you can say that one of them is a multiple of the other, and so they're linearly dependent, because you can just write v1 times 1 minus alpha, whatever you found for that, times v2. Okay? So anything higher than that would require us to do a little bit of work to show that they're all on the same plane or all not on the same plane if you're in R3 or higher. Okay, what else do we have for linear independence? A couple of other theorems. Some of these theorems I'm kind of just putting up here just for the sake of because they're in the book and are not really that important, but some are kind of important. If you can understand it mathematically, then that's great. If not, you have to find a way to see if you can restate the theorem in your own words so that you can understand it. So let's read the theorem carefully first, and then let's see if we can understand what it means. An indexed set S that contains vectors v1 through vp of two or more vectors is linearly dependent if and only if at least one of the vectors in S is a linear combination of the others. In fact, if S is a linearly dependent, if S is linearly dependent, the whole set, then v1 and v1 is not equal to the 0 vector, then there exists some vector later on, vj, that is a linear combination of the preceding vectors. Okay, who can restate that in their own words? Okay. You guys understand what he just said? He said if you have, there's one phrase there I want to change. So he said if you have a set of vectors and they're linearly dependent, you take one of the vectors and then you can write this one vector as a linear combination, not a scalar, but a linear combination of the other vectors. Then that's showing that it's actually dependent. Okay? So we had an example of a set that was linearly dependent. So let's see what that means for that particular set. So we said, I'm going to take out this more here. We said that this set was linearly dependent, right? According to this theorem, if this set is linearly dependent, then at some point, say the first one is not the 0 vector, that's clear, 1, 2, 3, right? And I could check that these two are not linearly dependent. How can I check if those two are not linearly dependent? Are they scalar multiples of each other? 1, 2, 3 equals alpha 4, 5, 6. According to the first components, alpha should equal to 1/4, right? But 1/4 times 5, does that equal a 2? No, so it doesn't work. So they are not scalars. So these two are still linearly independent. So that means we found that this set was dependent, right? So that means I could take 2, 1, 0 and write it as a linear combination of 1, 2, 3, and 4, 5, 6. So let's see. I don't know. I'm going to guess here. I don't want to guess. Can somebody just tell me? -2 for what? Does that work? There you go. That's what this theorem is saying. Right? So if you had more, it'd be more interesting. But we had something in 3D and happens to be linearly dependent. So there you go. So that's what that's saying. So if and only if means that if you can write one of the vectors as a linear combination of the other vectors, then it's dependent and you're done. Or if you know it's dependent, then at some point you're going to be able to write one of those vectors as a linear combination of the other vectors that you've already listed. Okay, that's what that theorem is saying. Questions? All right, we having fun yet? Whatever. Not so fun if you're just watching somebody explain stuff to you. It's funner if you could do it on your own now. Anyways. A couple more theorems that we should look at that was stated in your textbook. These notes, by the way, are just coming directly from your textbook. I just take all the theorems, the definitions and stuff, and then put them in the notes. Just pretending that I have really good notes. But I just copied it. All right, in the set containing more than one vector, there are entries for each vector. If a set containing more vectors than there are entries in each vector, so that's kind of like however many, what the components are in each vector, then the set is linearly dependent. That is, if you have a set of vectors v1 through vp in Rn, and p is bigger than n, then your vectors are linearly dependent. What? Let's go back to 2 dimensions. 1, 2. Are these linearly independent? I hope so. Yeah, they're linearly independent, right? If I throw a third vector, can I find another vector here that is independent from these other two? No, just no. That would make this independent. Can I find another vector so that these 3 vectors would be independent? Then they're going to be, yeah. So they're going to have to be dependent. Actually, can I change the vectors? Well, I don't have to ask your permission. I'm going to change it. Just to make things easy. So I'm going to change it to our standard basis vector, these things that we call our standard basis vector, just because it's easier to deal with. So 1, 0, and 0, 1 clearly are linearly independent, right? I can't multiply one by a scalar and make it look like the other. So now the question is, can you find another vector that's going to be linearly independent from these two? So any vector you choose, let's choose a random vector. Somebody throw out a couple of numbers. Or 5, right? Regardless of what you choose, you can always write 1, 0 and 0, 1 as a linear combination of each other. That would give you 4, 5. So you can always find these values, and the way I chose those two vectors, I made it easy for myself. So now I just say this is 4 and this is 5, and then that gets me that vector. So regardless of what you choose, in fact, if you just call this A and B, regardless of what you choose, it's going to be linearly dependent. A third vector in 2 dimensions, you only have 2 entries here. If you have a third vector in 2 dimensions, then it's going to give you a linearly dependent set. So in this case, n, in this example, n is equal to 2. Maybe I shouldn't draw. N is equal to 2 and p is equal to 3. We're trying to put 3 vectors in 2 dimensions and make it independent, and you're always going to fail because that can never happen. Okay? So that's what this theorem is saying. If you're in R4, the maximum number of linearly independent vectors you can get is 4. If you're in R4 and then there's 5 vectors, then that has to be dependent. Yes?
So if you have a linear combination of some set of those vectors, then they will lie on one 2-dimensional plane.
If we're on R2, because we're talking about planes, yeah, so
as the dimensions increase, go to space.
Yeah, so we can only go as far as we can see. Beyond that, we have to imagine. So R1 is just a line, a number line. So that's what we studied back when we were in 3rd grade or whatever. So that's R1. And if you're in R1, your object is going to be a line. It's a 1-dimensional line. If you're in R2, then you get a plane. So whether you're in R2, if you have 2 vectors that are linearly independent in R2, then you're talking about the whole plane. If you have 2 vectors in R3, then that's a plane in R3. If you have two vectors in R4, you can't visualize this anymore, but you have to imagine there's a plane, a 2-dimensional plane in R4, or R5 or R6, etc. Now, if you're talking about 3 vectors, 3 vectors in R2 are going to be dependent. This is our classic example of that. But if you're in R3, the 3 vectors that are linearly independent will span everything, the whole space. So we'll call it a 3-dimensional space. Okay. Now, if you take 3 vectors in R4, what you have there is a 3-dimensional space in 4 dimensions. So in 4 dimensions, there's another dimension that's not going to get covered. Wow. Whew, that's pretty deep right there. Yeah. Say it again? Yeah, you can see it that way. If you write this as a system, or if you write this as a matrix and row reduce it, you know, those are your keys that you're going to see that there's going to be a free variable. So we'll have a free variable. You guys are getting used to my writing already, right? I also try to say it as I write it, so if you don't understand my writing, you can go watch a video. Okay, so that's Theorem 8. Let's. There's one more theorem here. This one kind of follows from our zero vector discussion and then Theorem 8. If you have a zero vector in your set, then the set's automatically going to be dependent. Not much to say there. Okay. All right. So I have an activity for you. I have my my curl rotation for Calc 3. Surface oriented outward or inward. Anyways. Grab a vector and pass it down. Yeah. So in this activity, U will be a four-dimensional vector. Okay. What I want you to do is, as quickly as you can, I don't have any prizes. I should have got prizes. Is to find the largest linearly independent set of vectors by finding other vectors that are linearly independent from you in your group. So you want to get a posse that's linearly independent. Okay? Oh. Maybe I should stop this now. So first, let's talk about a transformation. A transformation is really just a function. Function is something that we've already dealt with, and we can think about all the functions that we know as transformations. So a transformation, a function, or a mapping, except the ones that we have studied before in Calc 1, pre-calculus, Calc 1, Calc 2, have been functions that go from a one variable to one variable. It goes from R to R. So all the functions that you've known, functions we know, are usually denoted with f, and then we say f of x is equal to y. So the x is the domain that comes from one variable, and the y is the range or codomain or whatever they call it here that comes from another one variable. So this takes your x values and gives it y values, at least the notation that we normally use. So now we're going to take a look at transformations that come from one higher dimension to another higher dimension. So a transformation is going to be a function, and we'll call it t for transformation, and it goes from a space, Rn, that's more than one dimensional space, and it goes to another space, Rm. Now the m and n could be the same or could be different. So it depends on how it's defined. So Rn to Rm is a rule that assigns to each vector in Rn, which is a domain, another vector in Rm. So the set of vectors where you're picking from is called the domain, and where it goes to is called the codomain. Again, sometimes it's called range. This should be bold-faced also, because this is another definition. For each x vector in the domain, the vector t of x in the codomain is called an image. And the set of all images is called the range. So they're calling this a range. So again, trying to relate with something that you already know, I hope. I hope you already know this. An example would be keeping the spirit of this. An example of a transformation from R to R, R1 to R1 would be something like f of x is equal to x squared. Okay, you're taking x values and you're getting y values, which are the squares of those values. Now, according to the definitions here, the domain are all possible values you can put in for x. I can put any number I want. So I can put in any number I want, any real number in there, and then it's going to do whatever it's going to do. Now, my codomain is essentially going to be wherever it gets mapped onto. But now they make a distinction here to call the range to be just the image of all possible values in the domain. So what is the range in this case for my function? What? What possible real numbers am I going to get from my output? What? Positive, including 0, right? Is that what you said, Ting? I didn't hear you. But you can't have negatives, so that's a main difference. So values that are bigger than or equal to 0, or you can just say whatever the notation is. So that's officially that's the definition for your range. So your codomain is all the possible values. Now, some of the possible values probably won't get hit by the function. And so if you want to count only those things that get hit by the function, that's going to be your range. Okay? Any questions? So this is an example that I'm hoping that you already know. And I think this should have been done in pre-calculus, the whole idea of domain and range. So let's take a look at what this means for us in RN business. So let's make up an example of a function t that takes in something from let's say R2. I'm in R2 here because I have a vector that has 2 components. And then let's send it to something in R3. So I'll say x1 plus 3x2. I'll say cosine of x1 and x2 plus e to the x1 power is an example of a transformation. So this is a transformation. Let's see if we can break this down. T is a transformation that takes vectors in R2 and then sends it to vectors in R3. I don't know what happened to my x1, x2 here. Oh well. Oh, let's see if we can find some examples. Where does 0, 0 go to? Zero, 1, 1, right? You put 0 for x1, you put 0 for x2, and you get your output, whatever that is. right? So 0 plus 3 times 0 is 0. We have cosine of 0. That's 0. No, that's 1. And then we have 0 plus e to the 0 power. E to the 0 power is 1. Okay? So another example, maybe if we take 0, 2. Where does this go to? What is it? 6, 1, and 3, right? So those are some examples. I would say that according to the definition, we could say that this vector in R3 is the image. This is T of 0, 0, image of 0, 0. This is T of 0, 2, which is the image of 0, 2 as it goes from R2 to R3. Quickly, what's a domain? So the domain would be anything that I can put in there. It looks like the cosine and the e are the weird functions, and I can put any number in for cosine or e, so that's all. The domain can be anything in R2 you choose. The codomain is R3. The range, well, we'll have to try to figure out what the range, finding the range is a little bit more difficult here. But if you think about it, and if you find it, send me an email, let me know. Then I'll give you some candy. All right, it's 2 o'clock, so we're done for today. Next time we'll pick up and talk a lot more about transformations. Thank you.